Hey everyone, and welcome. On behalf of Forge College, I am absolutely thrilled to have you here for another explainer. Today, we're cracking open a really fascinating architectural blueprint: cost models and execution drivers in EVM and SVM architecture comparison. If you've ever found yourself wondering, why your smart contract costs an absolute fortune to run, or how different blockchain architectures can charge you totally different amounts for the exact same operations, well, you're in the right place. Let's get into it.
Now, think back to our previous lesson on runtime constraints in EVM and SVM architecture comparison. We talked all about the hard limits of these networks, right? Things like instruction execution budgets, stack depth limits, memory caps. But here's the thing. Those limits are really just abstract rules floating out there in the ether. At the end of the day, someone has to pay for the actual physical resources being used by the network. So the question we're asking today, humorously, but also very seriously, is who actually foots the bill for these strict environmental limits? Spoiler alert, it's you. You, the developer, and your users. Let's dig into exactly how that happens.
So here's our game plan for today. First, from constraints to cost. Second, the three main cost models. Third, EVM versus SVM trade-offs. Fourth, building a token marketplace. And finally, developer workflow.
All right, jumping right into section 1, from constraints to costs, or translating limits to bills. You see, a blockchain can't just politely ask you not to hog all the memory. It needs to actively discourage you by hitting your wallet. Billing is the translation of a physical constraint into a code-changing cost signal. Let's look at this table to see how that works across three dominant accounting patterns: opcode-level metering, per-storage or rent billing, and aggregation effects. Just look at how compute is handled. In opcode metering, you're paying direct, immediate gas units per operation. Boom, right away. But under a rent model, compute isn't always billed per op, it might just be an implicit cost. Now look down at storage. Opcode metering hits you with a massive immediate gas fee for writing data. A rent model, on the flip side, charges you an ongoing fee just for holding those bytes over time. It's the exact same data, but totally different math.
Which brings us nicely to section 2. EVM versus SVM trade-offs. I love calling this the taxi versus the landlord.
Let's start with the EVM approach, which is opcode-level metering. Honestly, this is exactly like riding in a relentless, totally unforgiving taxi cab. Every single thing you do, every low-level operation, every loop, every bit of arithmetic, the taxi meter clicks up, cha-ching. The runtime maintains tight, absolute control over the CPU by charging you for every single deterministic ounce of work you do during the ride. If you're building in this taxi cab environment, there are specific instruction-level contributors you absolutely need to track. Heavy arithmetic and cryptographic opcodes? Yeah, they will drain your wallet fast. Storage reads, or S-loads, and storage writes, S-stores, are notoriously expensive too. But here's the really sneaky one: memory expansion events. In the EVM, if you expand your memory, that cost lingers. It actually increases the fare of your subsequent memory access for the rest of the transaction. It's literally like spilling coffee in the taxi. You can't undo it, and you are paying for the mess.
Now, let's switch gears. Welcome to SVM-style platforms, or as I call it, the strict blockchain landlord. Here, we're talking about rent exemption. Listen, the landlord honestly does not care how many push-ups you do inside the apartment, meaning your ephemeral computer's relatively cheap. What the landlord cares deeply about is how much square footage you're taking up long-term. You either pay a one-time rent that buys a persistent storage allocation, or you pay ongoing rent proportional to your exact storage footprint.
We also need to briefly touch on transaction-aggregation. If the EVM is a taxi, aggregation is a carpool. By bundling operations, you can save on fixed overheads, things like signature verification, by amortizing the cost across multiple actions. You're just splitting the base fare. But a quick word of warning: be careful. While carpooling saves on fixed fees, it can dangerously magnify your peak compute and memory usage in a single transaction. Do that, and you might hit a runtime cap and cause the entire transaction to revert.
All right, section 3, building a token marketplace. The showdown. Let's see this in action.
What's really fascinating here is how abstract theory completely alters our real-world code. Imagine deploying a token marketplace contract. Comparing these two choices shows a massive shift in strategy. Over on the left, EVM Model A uses a single storage mapping inside one contract. Every single time you list a token, you're paying high per-byte opcode fees, so your developer focus, aggressively compress your fields to save on immediate gas. Now look at SVM Model B on the right. It uses individual accounts per listing.
The immediate compute fee is tiny, sure, but now you have long-term rent obligations for every single account you open, so your focus completely shifts to designing compact layouts and lifecycle management, basically explicitly closing accounts when a token delists so you can get your rent deposit back.
So what happens during a high-load burst? Say a massive NFT collection drops, thousands of listings happening all at once. Under the EVM model, the network gets congested and immediate per-transaction gas fees spike through the roof as everyone bids for block space. You might even hit block gas limits. Under the SVM model, the immediate fees stay relatively low, but suddenly you're ballooning the network-wide long-term ledger storage. That creates massive pressure on the nodes and potentially higher baseline rent later. It's the exact same hype, but completely different systemic bottlenecks.
Moving into Section 4, Developer Optimization Workflow. Time to align our code with these costs.
Understanding the taxi and the landlord is great, but let's convert this into a practical workflow you can actually use. Step 1. Measure and categorize. Figure out, is my bottleneck compute sensitive or storage sensitive? Step 2. Match the pattern to the cost model you're building on. Step 3. Prototype and profile. Seriously, build a minimal version and run it on a testnet. Step 4. Select hybrid strategies. Most production apps blend approaches, like storing lightweight anchors on-chain and heavy JSON payloads off-chain. And finally, Step 5. Monitor and iterate. Keep a very close eye on those on-chain metrics after you deploy.
And this brings us to a brilliant heuristic. If you take away just one sentence from today's explainer, please let it be this. Compress when long-term bytes dominate. Batch when fixed fees are large. Pre-compute when per-op metering is strict. Memorize that. Keeping that rule in your engineering checklist is a total game changer for turning abstract cost signals into reliable, repeatable implementation choices.
All right, let's wrap this up. Our key takeaway? Cost models are simply the mechanism that translates hard network constraints into developer incentives. The taxi meter of the EVM and the landlord of the SVM demand totally different strategies. Dealing with the taxi? Avoid repeated heavy loops and excessive state rights. Dealing with the landlord? Optimize your data layout, use off-chain pointers, and please, clean up your unused accounts.
I want to leave you with this final, provocative question. Will you batch, compress, or pre-compute your next transaction? Think carefully about the architecture you're building on. If you want to dive deeper into this subject and explore more incredible Web3 topics, I highly encourage you to visit forge.college. In our next explainer, we're going to look at the exact profiling tools you need to capture gas and memory traces in realistic transactions. On behalf of Forge College, thank you so much for joining me today, and I'll catch you in the next one.